Hello everyone, welcome to my class. And in this session we are going to discuss the discrete common source amplifier. Now here is the typical configuration for discrete common source MOSFET based amplifier. And in this configuration we have a single voltage supply, and the gate voltage is biased through a voltage divider, and we have a resistance Rs at the source LED. And in these circuits we will feed in our signal through this CC1 capacitor here. The purpose of this capacitor is to isolate the DC components from the signal source, and the signal is fed out through the CC2 capacitor, and the CC2 capacitor also serves as isolation of the DC voltage, because this DC bias is very important. And this CS here is to bypass the IS. For AC signal, this RS here is being equivalently to be shorted by this capacitor here. Now compare to the BJT common emitter amplifier, you can see this configuration are pretty much the same. There's almost no difference. The only difference is here, and we don't have any gate current. But in the BJT common emitter amplifier, we have a very small base current and into the base of the transistor. Assume the capacitors of CC1, CC2, and CS, and they are larger enough so that their reactance are very small at the frequency of operation, and then the equivalent small signal circuits is shown below here. Now this is based on a hybrid pair model. Now we can see there's no current into the gate. And from this small signal model, we can do a couple analysis. First, to calculate the input resistance and also the output resistance, and we can also be able to calculate our gain here. As we did in studying a BJT amplifier, and we can calculate the following quantities for MOSFET based common source amplifier. So the value we are going to calculate include the input resistance Rin and output resistance Rout, and the partial small voltage gain AV, and overall small voltage gain GV. Now let's go back to the slides of the small signal model to see how can we calculate the input and the output resistance. Now from the input side, we can see since there's no current into the gate, so the input resistance can be easily calculated, which is the RG1, RG2 in parallel. For the output side, and we can use the Thevenin equivalent analysis. And in the Thevenin equivalent analysis, so this current source needed to be disconnected. And then we only left with RO, small RO, and RD here. Now the output resistance equals RD in parallel with small RO. Now our output voltage now becomes the current, that is GM times VGS, and times the overall resistance of these three. They are in parallel. And we have a negative sign because the current is flowing from the ground and back to the transistor. And from the input side, the input voltage Vi now actually equals VGS. And Vi can also be calculated from the signal source through this voltage divider equation. Now with this information, we will be able to calculate the partial small voltage gain AV now. is the output voltage equals here, and our input voltage equals VGS, and we plug in the definition of the AV, which equals VO divided by VI, which will give us the partial small voltage gain AV equals negative GM, and RORD RL in parallel. To calculate the overall small voltage gain, we can do the similar analysis as we did for BJT-based common emitter amplifier, and we can derive the expression of GV in terms of AV by the definition. Right, GV is the overall small voltage gain, which is the output voltage divided by the voltage at the signal source. And if we rewrite, and we can get this GV equals VI divided by V signal times AV. And VI divided by V signal actually come from the voltage divider equation. And we can write down this equation by plugging this in, and also plug in the AV. Eventually we will be able to get our overall small voltage gain from this formula here in the red color. Sometimes we put a resistor at the source without bypass by the capacitor CS. And this is called amplifier with source degeneration. And here is the configuration. Typically in this configuration, we will have a dual voltage supply, which is VDD and negative VSS. And in this case, we can use a current source to bias the transistor. Now, this current source can be made from a current mirror. In this case, we can use a T-model to model the circuits. And a T-model will simplify the analysis. If we can ignore the output resistance of the transistor. And from here, and we can easily get our input resistance, Rin equals Rg, because there's no current into the gate. And we can also easily to get our output resistance, Rout equals Rd, by looking into the circuits from here, because this is the current source we need to disconnect. And we're only left with Rd because we already ignored our output resistance of the transistor. So only left with this ID here. To calculate the partial small signal voltage gain AV from the outside of the small signal circuits, we will get the output voltage. It will be very similar as before. The only difference is now we ignore the small RO here. And at the gate, we find through the voltage division, and we have this VGS signal will equal 1 over Gm divided by 1 over Gm plus Rs times Vi. Now let's go back to the small signal model here. Now here, from gate to the source is our VGS. And from the gate to the ground is our Vi. So from Vi to the VGS, it is go through this voltage divider here. One resistance is here is 1 over Gm. Another resistance here is Rs. So basically this is a voltage divider equation. By plugging in this VGS and into this output voltage, and then we will be able to figure out our partial small signal voltage gain AV equals the negative Gm Rd in parallel with IL divided by 1 plus Gm Rs. And similarly, we can calculate our overall small signal voltage gain and GV as we did previously. Once we plug in the voltage divider equation as well as our AV, and then we end up with the overall small voltage gain and with this expression here in the red color. Now adding the source degeneration resistor Rs here has a number of effects. So the first, it lowers the small signal voltage gain. Now this can be easily seen from the gain formula here, because we have this denominator now is bigger than 1. Originally, we don't have this. We don't have this denominator. Now we have this denominator, which means this is bigger than 1. It will reduce our overall gain. Now, even though the gain is reduced, we still have some benefit. So the major benefit is that the small signal voltage gain becomes less dependent on the device characteristics. For example, if our GMRS here is larger enough, we see it's much larger than 1, because this is a larger value, and then we will be able to ignore this 1 or neglect this 1. Once this is neglected, and then we will be cancel this GM from the numerator and the denominator. Now we end up with overall small voltage gain is only governed by those resistors in the circuits. It becomes no longer dependent on the transconductance of the transistor. Now this is very important, right? Because for these transistors, due to the fabrication variation, you might have a different transconductance. But with this configuration, we will be able to make our amplifier less dependent on this GM, and the gain will be only dependent on the resistors we are choosing for this amplifier. Now we can have an example on how to analyze this discrete common source MOSFET based amplifier. And in this single supply common source MOSFET based amplifier, and with degeneration, and all those resistance actually has been provided in this configuration. And what we are asking to do is to analyze the input resistance and the output resistance, as well as the overall voltage gain. When the degeneration resistance Rs now equals 0, right? When this is equals 0, so there's no degeneration. After that, we will do further analysis. In order to improve the linearity of the amplifier, we are going to reduce our VGS to half of its previous value. And then this can be achieved by adding this degeneration Rs resistor here. And here we were asked to find out how much this Rs can make our VGS and becomes half of its original value. And finally, we will calculate our overall voltage gain again. Now, it's pretty straightforward for the non-degeneration common source amplifier to calculate the input resistance. We just plug in the value of RG1 and RG2, end up with 1.6 mega ohm. And the output resistance can be calculated by this RD in parallel with small RO. It ends up with 16.5 kilo ohm. So the overall small voltage gain can be calculated based on the equation we derived. We plug in those numbers, we will get its value about negative 7.1. Now once we add the degeneration and the source resistance Rs, now the VGS now will become Vi divided by 1 plus GMRS. Before we add this Rs, our VGS equals Vi. Now that means in order to reduce VGS to half of its value, and this 1 plus GMRS needed to equals 2. Now from this formula here, and we are able to calculate our Rs. And Rs equals 1 over Gm. 1 over Gm equals half, it's 0.5 kilo. Now, if we neglect this small Ro, our GV now can be calculated from this formula. This is what we derived earlier. If we plug in those values, and we see, and our gain actually is being reduced. It's almost half of our original gain. Okay, I think this concludes this session. In next session, we are going to discuss the CMOS common source amplifier. So when we configure the MOSFET based amplifier in a common source configuration, but in the integrated circuits. I'll see you in next session.